Hello to all my viewers. This is Dr. Dhaval Maheta, and today we'll understand how to run factor analysis in STATA. Factor analysis or a principal component analysis is a data reduction technique to reduce a large number of variables into fewer number of factors. These techniques are used in the analysis of the validation of constructs, creating measurement index, scale construction, and data reduction. Now let's try to understand the concept of factor analysis by this pictorial representation. On the screen, you can see the different means of communication. There are some commercial vehicles, there are some private vehicles, and the bicycle. Let's club all commercial vehicles together, all private vehicles together, and the bicycles together. Now let's say that the positive x-axis represents the private transport. Negative x-axis represents the commercial vehicles. Positive y-axis is a two-wheeler. Negative y-axis is a four-wheeler. So, all the means of the communications will be segregated into the four quadrants. If we talk about this quadrant, it is two-wheeler, private transport, and that is a bicycle. If we talk about this quadrant, it is a private transport four-wheeler, that's a private vehicles. And this quadrant is commercial vehicles four-wheeler. So the entire so all the means of communications are segregated into four quadrants. So this is the same concept of factor analysis, and that's the reason it is known as a data reduction technique. Factor analysis is used to identify one or more common domains for a group of correlated variables. Factor analysis is a technique used to identify the pattern of correlations or covariance between the observed measures. For examples, indicators of job satisfaction, political attitudes, self-esteem, socioeconomic status, health, or family values. There are some assumptions for running the factor analysis. We start with the first one. As far as the measurement levels of the variables are concerned, interval or ratio variables form the input for a classical factor analysis. With regard to the number of observations necessary for the performance of the factor analysis, one may say that for every variable, there is at least 10 times as many observations that is, the respondents are necessary. Some thumb rules for the sample size. We start with the first one, 10 cases per item in the instrument. It means that if the number of variables are 20, so 20 into 10, 200 observations are necessary. Subject to variable ratio should not be less than 5. Subjects means the observations, and these are the variables. 5 times the number of variables or 100 minimum. Minimum of 200 cases regardless of subject to variable ratio. So there is one case study. Automotive manufacturer sought to refine its product development and marketing strategy. While they regularly track the consumer ratings on dozens of individual vehicle features, they lacked insight into how these attributes were grouped together in the consumer's mind. So first of all, let's load the data set. So go File, Import, Spreadsheet, Browse, Factor Analysis, Open. Import first row as the variable names and click OK. On right hand side, you can see the name of the variables. So the price of the car, mileage of the car, maintenance, comfortable, leg space, brakes, collapsible steering, power steering, interiors, and space available. Run the command browse to see the entire data frame. Okay. Now we will run the factor analysis. So for this, go in statistics. In this multivariate analysis, in this factor and principal component analysis. So here we are having option to run factor analysis or the principal component analysis. Click on the first one, factor analysis. From here, you will have to select the variables. Don't select the serial number as it is not the variable. Click on price, mileage, maintenance, comfort, leg space, brakes, collapsible steering, power steering, interiors, and space. Now click on the model 2. So some methods which are available are principal factor, principal component factor, iterated principal factor, maximum likelihood factor. So either run principal factor or the maximum likelihood factor. We will go for the first option. Maximum number of factors to be retained. I can specify how many factors are to be extracted. Minimum value of eigen can also be specified here. Click on the reporting and activate this one. Display loadings as blank when absolute value of loadings is less than 0.5. Now click OK and your results are ready. So you can see here factor, eigenvalue, difference, proportion, and cumulative. This I will explain later on. And here is the factor loading. Now again go in statistics, multivariate analysis, factors, post estimations, and if I want to rotate the output, that is if I want to introduce the Varimix rotation, this can be done from here. Rotate the loadings, but this we will see later on. First of all, click on this scree plot of eigenvalues. Click here and click OK. So you will get the scree plot. The same scree plot you can get from here also. Graphics, multivariate analysis graphs, scree plot of eigenvalues. Click here and click OK. Now, so now I want to generate the KMO, that is Kaiser-Neo-Olkin measure of sample adequacy. So KMO is a test conducted to examine the strength of the partial correlation, that is how the factors explain each other between the variables. KMO value closer to 1 are considered ideal, while values less than 0.5 are unacceptable. Recently, most scholars argue that a KMO of at least 0.8 are good enough for the factor analysis to commence. So here is a range, KMO greater than 0.9, marvelous, between 0.8 and 0.9, meritorious, 0.7 to 0.8, average, 0.6 to 0.7, mediocre. So from where I can generate this result? We will go in statistics, multivariate analysis, post estimation reports in statistics. Click here and click OK, and we got the results. Now let's do the interpretation of all these outputs. We start with the first one. The overall KMO statistics is 0.63. This falls into the mediocre or a moderate range according to the conventional benchmarks. This means that the dataset at a global level just barely acceptable for factor analysis. While not strong, it does not suggest that the proceeding with the factor analysis is not entirely inappropriate, but the results should be interpreted with some caution. Next is we want to do the interpretation of this output. So it's here, this one. Now what you have to see is factor 1, its eigenvalue is 3.87, factor 2, 2.44, and factor 3, 1.19. So as per the eigenvalue, 3-factor solution is better because we consider that the eigenvalue should be more than 1. Now we are having the factor loadings, factor 1, factor 2, factor 3. Now let's do the interpretation. The factor analysis reveals a clear underlying structure in the data with 2 to 3 strong factors emerging. The most definitive evidence comes from the scree plot implied by the eigenvalues. The first factor, this one, its eigenvalue is 3.87 and it accounts for nearly half of the common variance. So here is it, 49.75, indicating a dominant primary dimension. The second factor, eigenvalue, is 2.44. It's also robust, explaining an additional 31.35% of the variance, and its cumulative is 81%. The third factor, its eigenvalue is 1.19, which just meets the Kaiser criterion, adding another 15.32 to the variance explained, and so the total variance explained is 96%, which is quite good. However, the substantial drop in eigenvalue after the second factor and the fact that subsequent factors explain minimum variance, with eigenvalues falling well below 1, strongly suggests that either the two-factor or a three-factor solution is the most parsimonious and interpretable. The model would explain over 80% of the common variance with two-factor solution and 96% with three-factor solution. Furthermore, the highly significant likelihood ratio test, this one, and its p-value is less than 0.05, provides a strong evidence that the observed variables are not independent and the factor model is a significant improvement over a model with no common factors, confirming that the correlation among the variables are meaningful and suitable for factor analysis. We can carry out the factor analysis. Now we will give the name to these factors. This is factor 1, factor 2, factor 3. Let's see in factor 1 which are the variables: price, mileage, maintenance, and space. The factor analysis successfully identifies three distinct and interpretable dimensions that consumers use to evaluate vehicles. The first factor, economy, we will give the name economy to the first factor, is a robust and clearly defined dimension encompassing both immediate and long-term ownership cost. It is characterized by very high loadings from price, mileage, maintain, and space. This indicates that the potential buyers strongly associate the purchase price, fuel efficiency, and maintenance cost as a single cohesive aspect of vehicle's economic value. Second factor, factor 2. The second factor, spaciousness, captures the vehicle's interior volume and the comfort. It is defined by a very high loadings on comfortable 0.81 and leg space 0.757 and interiors. So I'll have to change a figure of interior, just a minute. So it's 0.77. All these factors reinforces that the quality and feel of the cabin are perceived as a part of the overall spacious and comfortable environment. The third factor, safety, is defined by core safety and structural features. It has a significant loadings from brakes 0.59 and collapsible steering 0.56. So this is a scree plot. The scree plot is a graphical tool used to determine the optimal number of factors to retain. It displays the eigenvalues of each factor in the descending order. So on y-axis you can see the eigenvalues, and these are the number of factors. Normally the scree plot is elbow shaped, so wherever it's kinked, we consider that many number of factors for our analysis. Or the another method is how many factors are above the eigenvalue 1. Please see this carefully. This, how many factors are above the eigenvalue 1. So here you can see 1, 2, and 3. And that's the reason three-factor solution was considered for our analysis. The elbow of the plot, the point where the curve bends and slope flattens out, and it indicates the point where additional factors contribute little explanatory power. So basically it's plotted on the basis of these values, 3.87, 2.44, 1.19. We should retain the factors that appear before the break in the slope, that is the elbow. In a typical plot like this one, The first few factors have a high eigenvalues and the line is steep. This is followed by a point where the slope becomes less steep and forms a more gradual tail or scree, like the rubble at the base of a cliff. This recommended number of factor is where the elbow occurs. For example, if the elbow is after factor 2, you would keep two factors. It means that, see, this elbow is after factor 3. So you will keep three factor solution. If the elbow is after factor 3, you would keep three factors. In this case, we would retain either 2 or 3 factors depending on where the exact elbow appears on actual plot. We would combine this with either other criteria like Kaiser criterion, there's an eigenvalue greater than 1, and the interpretability to make the final decision. Now in case, if you don't get the proper output, so what you will do, you will go in statistics, multivariate analysis, factors, post estimations, rotate the loadings, and here you can activate the Varimax rotations, click OK, and you got the output. You can see here. In case if you don't get the proper factor loadings, you can give the rotation. So this was all about how to run factor analysis in STATA. For more videos on STATA, kindly refer to my playlist. I also uploaded many videos on data science, machine learning, and artificial intelligence on my YouTube channel named Dhaval Maheta. To watch the full videos, please subscribe to my YouTube channel and check the playlist. Please don't forget to like and share my videos. You can also follow me on different social medias, link given in the description box.